Okay. Okay, guys. This chapter is about, okay, guys, the chapter is about applications of derivatives. You've already seen one with related rates. These are going to be some other ones. This is a theorem that you're going to use. It's on extreme values, and it's one of the most important theorems that you're going to have on the exam. I've almost always seen it in a free response question. We will be using our graphing calculators to look at some of these graphs. But on the exam, and they've done this, in the section where you're allowed to have a graphing calculator, they asked for a maximum value of the function. And students graphed it. You got 0 points for that. You had to do the calculus. Okay? So that's one reason why this is going to be really important. But it's also just a nice little theorem. And I don't like the handout on this particularly because it seems to be missing stuff. So I'll go through it, but probably skip some things too. We're going to do some vocabulary. We're going to find out what an absolute and global extreme value is and a local relative. Now, it's extrema because that's plural for extremum. It's Latin. Or you can just say extreme values. We're going to find out how you find extreme values, and extreme values are max and mins. You've done this before, okay, Stephen? In pre-calc, except you graph to find the maximum value of a function. Now we're going to use calculus. You may need to use both. We are also going to find out what critical points are and do the extreme values theorem and when we apply it. Okay, Stephen? Okay. Here's a function. And, okay, you guys? What are extreme values? They're the max and mins of the function. They are not the x-coordinates. Look, did you just sit someplace else? They are not the x-coordinates. They're not where does this occur. They're asking what they are. So if I look at my picture here, is there a maximum value of this function? And is there a minimum? Well, I'm just going to write it up here. What is the maximum value? It's right here, right? About 2.5. Haley. I know we're going to do this. If you want to get your quizzes back today, we can. What's the minimum value? What is it approximately? Looks like it's about here. Negative 2.9 or negative 3 is close enough. Now, there was something interesting about this maximum value. What's true about the derivative here? F prime of my maximum value is equal to 0. So that's one place that we can look. Okay, Haley, Stephen? It's one place we can look for maximum and minimum values of a function. What's true about this? This is an endpoint. That's another place to look for maximum minimum values. Okay, what about this other endpoint? Is that a max or min? No. Okay, Noah? Then we have what we call local max mins. Maybe that's why nobody wanted to listen because they already knew it. This is a local one. This is also even though this is the biggest one, it's also a local and it's also a global. Now, what do you mean by local? It's who's the biggest one in the neighborhood. So we could talk about Christmas lights. We could talk about the Christmas lights in this neighborhood. Who's got the best lights? You do? I have the best lights in my neighborhood. However, they're pretty pathetic. But compared to some of the places in Minneapolis, there's some really nice ones, right? So we got global max and we got local max. true. There's a lot of discussion about whether this is a local minimum or not. Actually, it is. Okay, Noah? I agree. I look at this and say, in the neighborhood, well, I don't have the left side of the neighborhood, right? Okay. This has the neighborhood. I've got to look at the neighbors on both sides. And literally, it's called the neighborhood in math. Literally, that's in that neighborhood. That is the biggest value, but of the whole picture, it's also the biggest. So it's global. Now, and there's been a lot of discussion, but I did ask this on my listserv, and yes, the endpoints are considered local. I'd say, well, I don't see how you can say that because I can't see what the other side looks like. But this would be a local minimum. This would be also a local minimum besides being the global minimum. This is a local minimum. Because, and this one's easy to see, because in its neighborhood, that's the least. You go really close to this point, you look on either side, your neighbors. You look at your neighbors now you compare. In my little neighborhood, I'm the only one with light, that's why I'm the best. But if you go across 3 points, then there's a whole bunch of really nice lights over there, I'm not the best. This one, right here, because in its neighborhood, it's the biggest, and in my whole picture here, it's the biggest. Now, we're not going to worry about the endpoints. Even your textbook says the locals occur at endpoints, and just ignore those answers because it gets to be really confusing. They will never have local maximums at endpoints, not local. Now, the other thing they're going to say, Brian, is when they ask for a max or a min, they're talking about always a global. They have to say the word relative or local to be able to have that. Do I add it up here? So they actually have to say relative or local if that's what they want. If they don't say one of those words, then they always want the biggest one or the smallest one. Okay, Alexi. Okay, they might ask where they occur. Usually it's what is the value. And you're going to find out where it occurs. And how can you find it? We're looking at pictures here, but how would you find the maximum or minimum? Sophie? How would you find a max or min? We could consider what? Endpoints? And where the derivative is what? Is there another place? How about a sharp corner? Absolute value, that's a minimum. What's with the derivative here? Does not exist. Okay? Is that okay, Jack? These are where max mins occur. We're going to look at endpoints, if I have a closed interval. Other places, other candidates are where the derivative is 0 or where the derivative is undefined. They call those candidates. They're called critical points. Sharp corner, cusp, anything like that. Now, there's no guarantee that you're going to have a max or min there. What if I had this situation? What's true with the slope right here? M equals 0, but do I have a max or min? No. And we'll get to that. It's almost like the first 3 sections are kind of muddled together. The slope here is positive. It's 0 there, and then it's positive. What do you think has to happen for that to be a maximum or minimum? Can't go positive, 0, positive. It has to what? It has to change signs. Because if you look at this is positive, this is 0, and that's negative. Well, that's section 4.3 or something. And when we get through all those 3 sections, I'm going to summarize everything because it takes a lot for them to talk about it, and it really isn't that much. Okay, turn the page. looking at this picture here, it says define the following terms of the function. If I have a maximum value at C here, what's true about f of C? No, that's f prime of C is 0. But it's bigger than everybody else. And what we can do is you're going to collect data on derivatives, and you're going to be able to talk about a function. You may not know what the function is, but you certainly can find out where you have a maximum value or minimum. What if it's a minimum value at C? Then f of C is what? Smaller than all the other y values. And what's an, yeah, it's easy to write backwards. What's an extreme value? It's the maximum or minimum value of the function. Not where, but the value of f of x. And the hardest part, at least for me, is remembering I want the value, I want the y coordinate, not the x, not where it is. Okay, Sophie? Okay. Now, let's see where, oh, I'm sorry. Extreme value is the maximum value of the function or the minimum value of the function. Could be local, could be global. It's still an extreme value. If you think about what extreme means, it kind of makes sense. Can I slide it? Now, I would like to find when a max or minimum exists. I want to find conditions to guarantee that. Okay, so I'm going to draw my pictures here. Does this have a maximum or minimum value? Declan? Does that have a maximum or minimum? Some people said, well, I could get really close to this open circle, but you know what? I could still be closer yet. Can I ever get there? No. Well, we're going to look for conditions that we can guarantee it. Oh, let's look at open circle too. Is there a maximum or minimum value here? I didn't know that very well though. No. How about, is there a minimum? What if I do this? Do you guys need to sit someplace else? Yeah, put it in the bag. I don't think so. Okay, what about that? Do we have a max and min? Yeah. Here's your minimum. Here's your max. Now, what's the problem with all these graphs? Or what could be a potential problem? What was the problem with the first graph? They're holes. It's discontinuous. So I want to come up with a theorem that guarantees I have both a maximum and a minimum. So I have to have a continuous function. Now I have a continuous function here, and I still don't have a max min. What's the problem with this one? I need endpoints. Okay? Now, just because I don't have a continuous function, Alexi, does that mean I can't have max and mins if it's not continuous? No. There's an example. This is discontinuous, but has max and min. But what if you have a continuous function and on a closed interval, it has endpoints? Then there's a guarantee. And where will they occur? Where would you look for max and mins? Look for max mins At the endpoints, where else? Here's a max. No, what's true? Jack, what's true? What's with the derivative there? F prime of c is equal to 0. What about the absolute value function? F prime of c does not exist. Those are places to look. Okay, that's all we're going to do is we're going to look for max mins here. How do I know if I have a max min? This is called the max min existence theorem. There's really no place on your handout for it. But what would you do next? How would you know if this is a maximum or not? Yeah. See, find the value of that. See if that's the highest value. These are the only places maximum is going to occur. At endpoints, it has to be 0 or undefined. So all we have to do, this is the only calculus there is in this. That's it. The rest is not calculus. Evaluate f of x at these points. These are called critical points. You remember that? Yeah, Mr. Domin, I'm pretty sure you used the word. Hey, Alexi? James? Those are called critical points. So let's identify them. They're the endpoints. And actually, generally speaking, we don't call endpoints critical points. It's usually when the derivative is 0 or where the derivative is undefined. And then they have special names. Now, you don't have to know these special names, Sophie. The thing is there are like 5 theorems you have to know. This is one of them. This is a huge theorem. It's called the max-min existence theorem or the extreme value theorem. And that's what you're going to use on the exam. Well, but the students didn't. They looked at the graph and they didn't use this. So all you have to do is have a continuous function, closed interval, look where the derivative is 0 and where it's undefined, and then evaluate your endpoints and these places where the derivative is 0 undefined, and then see which is the biggest, which is the smallest. We'll do 2 problems. Now, special name here. I don't think they'll do this to you, but it's possible. So we have to get the vocabulary. Stationary points. Can you see, guys? Stationary points, and I'm sure you haven't seen that word before, is where the derivative is 0. Singular points, check, is when the derivative is undefined. Well, they might. Okay, and the endpoints on a closed interval would be A or B. A and B. Okay, so what do you have to find extreme values? What's the most important thing? What kind of function do you have to have? You have to have a continuous function. It has to be a closed interval. It has to have endpoints. Okay, it's not that hard to do. It's very little calculus. I just know that if I have a continuous function and it's on a closed interval, that I can find both a max and minimum. I might have to use my graphing calculator. Okay, here it is. That's the example we're going to do. Is this cube root, is that continuous? Yeah. Is it a closed interval? Okay, I've already graphed this, so I'll bring up my calculator. Do what? You're going to have to put some of this in your calculator because they're not going to be closed intervals. Like, is there going to be, like, I think, like 2 x squared plus y, give like move the y over? Yeah. No. Okay. So I put this into my calculator, which will save us a little time. Okay, Jack? There it is. And then I put the window from -1 to 1. Okay, you guys. Shh. You guys, this is not going to be easy for you algebraically. Calculus is the easy part. Well, maybe not. Okay, I'm going to graph it. There it is. Kind of a strange looking graph. Okay, Brian? That's what it looks like. Okay, so just look now. You would get no points for going to the graph on the calculator and saying you have a max min. Here's the minimum, right? And the max is either going to be this one or it's going to be this one, and honestly, I can't tell unless I evaluate it. Okay, Haley? So what we're going to do is we are going to apply the max-min existence theorem because it's a guarantee, Casey. It's like going and getting your car fixed when you have a warranty. Guaranteed. They're going to guarantee it. So I'm going to draw my little chart here, and I always start with my endpoints. You don't have to use a chart, but I think it helps keep you organized. So let's first find the value of the endpoints. Because that's all we're going to do. We have a continuous function, closed interval. We will find the critical points, and then we will evaluate them. So can we do f of 1 pretty easily, Jack? What's f of 1? Critical points. What's 1 to any power? Yeah. Okay, you guys? Should be working the problem ahead of me. What's 1 to any power, James? So what's this answer here? 6 take away 3 is... Okay, I always do the easy things first. That was the easy one. What's f of negative 1? Well, no, you got to be careful. I don't know what it is. Okay? Now, I don't care what that number is. You're going to raise it to the 4th power. Would that be positive or negative? Positive. So this is going to be 6. What's the other one going to be? Jack? Either one of you? What's negative 1 to the 1/3? What's the cube root of negative 1? Yes, you can. Can't square root negative 1, but you can cube root it. That's a negative 1 times a negative 3, so it's what? Plus 3. So this value is 9. So the question is, what's the other value? Okay, you guys ready? What? Yeah, that's 9. This is cut off. That's the reason why I can't see it. On my graph, if I go up here and I change my window, notice my y values only went up to 3.1. Let's make it 10. So this is the way your calculator lies. Hmm. Now look at the picture. I had it, you guys, I had negative 1 to 1 on the x's, but I didn't have the y's big enough. And it looked like they were pretty close in size here, but I didn't have the right height. So you're going to have to be careful with your graphing calculator because it lies a little bit. Okay, we now have to look at, where else? Where are the other critical points? So what calculus we have? What am I going to look for? The derivative. So I'm going to copy this down here. So 6x to the 4/3 minus 3x to the 1/3, right? Did I copy that right? Okay. James, how do I find that derivative? Yeah. Just the power rule. 6 times what? Okay, now we have to do some fractions, Sophie. Okay, guys. Alexi, what's this going to be when I subtract 1? No, what's the exponent going to be? 1/3. And this is x to the what? Negative 2/3. This is the only calculus. That was it. The rest of it is algebra. What's 6 times 4/3? Which is 8. Now, I don't like that x to the 1/3. I don't really know, I don't have a feeling for what that is. So I'll rewrite it as the cube root of x, which is not much better, but at least I have a feeling for what it is. What happens to the 3's here? They cancel. And so I'm going to get, I don't like that negative 2/3 either. So it's minus 1 over x to the 2/3. Well, I don't like that either. I subtracted 1 from 4/3. Mhm. Okay, you guys, this is the cube root of x squared. Now, I like the singular points. Which ones are singular points? Where the derivative is what? Where the derivative is what? Colin, what's a singular point? Casey, do you know what it is? That's right. It's where the derivative does not exist. Where does this not exist? Okay, so x can't be 0, but is that in my interval? Oh, yeah, it is. So guess what? We will evaluate our function there. That one's easy. What's f of 0? Not f prime of 0 does not exist, but what's f of 0? James, Declan. That's 0. Okay, is there a place when the derivative is 0? So we'll put this in here, and then we're going to do a homework problem. Now, I've always seen this to be true. They almost always just have 2 terms. So Noah, if I take one of those and put it on the other side, I'll get a proportion. I'm going to add the negative 1 over cube root x squared. So I'm going to get 1 over the cube root of x squared equals 8 times the cube root of x. How do you solve a proportion? Yes, you do. That's why I like it. You cross multiply. Well, you just multiply them together. So I've got 8 times the cube root of x times the cube root of x squared equals 1. And can't I take these radicals here and rewrite this as the cube root of x cubed? Oh, the square root of a times the square root of b is the square root of a times b. What do you do with exponents? They add them. So that will cancel out and just give me an x. So I said it's the algebra that's going to cause us trouble. So what's x equal to? 1/8. Riley, is that okay? Well, this is the hardest part. Then I have to find f of 1/8. And f of x was equal to 6x to the 4/3 minus 3x to the 1/3. That's the function. So you first decide if the function is continuous and you have a closed interval. You evaluate your function at your endpoints. Then you find where the derivative is 0 or undefined and evaluate your function, not your derivative, at those points. So, yeah. You could. But this has been on the free response. You probably will find it in both places. I had to use my calculator to look at it. Here's the thing I don't like about this textbook is that they put problems in here that are not closed intervals, and the only way you can see if it's a global max or min is to look at the graph. I'm going to do that. I just am saying that you may have to use your graphing calculator to look at some of these graphs. If it's a closed interval, it's a continuous function, no problem. Okay, you guys, let's do the easy one first. What's the cube root of 1/8? Well, what times itself 3 times gives you 8? 2. So that's 1/2. So then this one's going to be 6 times 1/2, because I always do the roots first if I can, to what power? 4. So this is going to be 6 times 1/16 minus 3 times 1/2. Can I reduce the 6/16? That's 3/8. Just fractions. Now, I got to get common denominators. What am I going to multiply this by? I want 8. 4. So I'm going to be 3 minus 12 all over 8. So it's what? Negative 9/8, which is negative 1.125, right? What are eighths? Eighths are 0.125. If you do any kind of measuring, you're going to be to eighths. We are evaluating the function at 1/8. Okay. What's the maximum value? 9. That's your max. What's your minimum value? Now, you could check this on your graphing calculator to see that you certainly can see that the maximum, but the minimum, if you want to check the minimum, you can. Now, like I said, if it's in the free response, it's fine. You can still check your answer, but you still have to show all the work I just did. It wouldn't be enough to go second, calculate, find the minimum. Won't do it. Okay, you guys, there it is. Notice where it occurs, but that's not what I want. I want the value. Okay, you guys, let's do a problem. Let's do a homework problem. Let's do number 11. Yes, you will. Now, I don't like decimals, so I'm going to use a fraction. I'm still going to need a calculator. Okay, Casey? I want to find the maximum minimum values of the function. First question, Riley, is it continuous? On that interval. No, it's not continuous. It's 0, but 0 is not in that interval. Yeah, that's continuous. Hey, Casey? Do I have a closed interval? This is a homework problem, you guys. Alexi, Declan, James. Okay, so we have a continuous function, closed interval. I need to find my critical points. Where are the critical points? Endpoints, and what else? Where f prime is 0 or f prime is undefined. Either way, they're the same thing. Okay, I just do what's easy first. Because, you know, if it's on the exam, you might get a point for just testing the endpoints, even if you don't do the calculus. So do the easy things first. Get as many points as you can. One endpoint is 1/2, and the other endpoint is 4. So what's f of 1/2? Well, it's 1 over x, which is the reciprocal. which is 2, plus the log of 1/2. Well, you know what that is. That's, sorry, using properties of logs, because you forget them, it's 2 plus the log of 1 minus the log of 2. Hmm? It'd be both, the horizontal line. What's the log of 1, you guys? No, it's 0. Yes, we reviewed the logs. You didn't do that assignment on the log review. You need to do that. Okay, Casey, what's f of 4? Oh, thank you. It's fine. I have it right on the other board. Well, that's what it is. We'll have to look it up. Well, let's use a calculator. Yeah. Okay, what's f of 4? Casey, what's f of 4? It's the reciprocal of that, so it's 1/4 plus the log of 4, whatever that is. Okay, now we'll do the calculus. Are you ready for the calculus? I'll rewrite it. F of x is equal to 1 over x plus the log of x. The calculus isn't that hard. Do you know, have you memorized, Colin, the derivative of 1 over x yet? Well, this is x to the negative 1 plus the log of x. Okay, what's that equal to, Declan? What's the derivative look like? This is just the power rule. Negative 1 times x to the what? Plus the derivative of the log, which is 1 over x. So that looks like this. Negative 1 over x squared plus 1 over x. Okay, where's that undefined? Because that's the easy thing. Zach? Where's that undefined? At x equals what? And guess what? That's not in our domain, so I don't have to think about it. Okay, Colin? Now what am I going to do? I want to see where this is 0. Can you just look at that and tell me where that's 0? Should you guess and check? Okay, say we can't do guess and check. Let's add this to both sides. This is where the problem's going to be. Now what do? Cross multiply. So x equals x squared. And I can't square root it. That's not going to work for me very well. When I added it to both sides, it becomes positive. Plus 1 over x squared plus 1 over x squared. And you know what I'm going to do? I'm going to get this. X squared minus x equals 0. Now, you guys, something that you may not realize is this is not the same equation. That's the original equation, Casey. No, would you put that away, please? Casey, this is the original equation. That doesn't look like it. However, numbers that make this true are candidates to making that true. And when I factor this, because we're going to learn a little algebra here, this is x times x minus 1. What makes this true? 0 or 1. Does 0 work in my original equation? No. So it's 1. But the point is that you're transforming this into something where you can look at it and see what the answer is. I could look at that and see 1 was the only thing that would work. There it is. What's f of 1? It's 1 plus the log of 1. So it's just 1. I need my calculator to do these guys. I don't know what they are. So I can't even answer the question without the calculator. So we're going to quit. Okay, we're going to quit, and we're going to find 2 minus the log of 2. And that's 1.3068. I'm just going to drag it over here. And then the other one, girls, is 1/4, which is 0.25 plus the log of 4. 1.63. Okay, so which is the max, which is the min? What's the maximum? 1.63. That's the max. What's the min? 1. This is your homework problem. No, we don't have the book. We're back in the old book. Don't throw it out. You have a final exam to study for. You have an AP exam to study for, and I want them back at the end of the year. Okay.